Hello, my name is Todd Rothman, and I want to welcome you back to Organic Chemistry 1. In this video, we're going to go over isomers. Now, this is just an introduction. The real meat and potatoes of isomers is going to come up after your first exam. But for now, we just have to have a good enough understanding so that we could draw chemical structures based on formulas given. Okay? So at this point, we have functional groups down. We know what functional groups we need to know for this exam. We also understand the basics of alkane, hydrocarbons, alkene, alkyne, and now we're going to just try to learn how to put these molecules together based on a formula. Okay? So here are the three sections, and let's get started. So the first thing is, I just want to emphasize, why are we learning about this now for when this is something that usually is an exam too? The only reason why we're learning about isomer, I'm talking about the isomer component, is because it's really important that you have a general idea of isomer, and I'm just going to refresh our memory from what we learned in Gen Chem. But again, we're not going to go into all the crazy details that you would normally expect to learn. There's a whole chapter on isomers, chapter 5, so you'll see all that detail then. But for now, let's just go into a quick review. So the first thing is, what is an isomer? So an isomer is where molecules have the same formula, but they're not the same. They have different properties, they have different structures, they have different, they're not the same, even though they have the same formula. Now, there are two types of isomers that we can think of. There are constitutional isomers. These are where we have connection differences, and then we have what's called stereoisomers. Those are the two types of isomers. Now, constitutional isomers, what we're going to focus on today, okay, with a very small touch on stereo, but mainly constitutional. So let's take a look at an example of constitutional. So imagine if you have the formula C4H7F. So that's our formula. And what we need to do is figure out what it would look like. So here are two structures that we put together on paper, for example, or maybe they're provided. And when you look at them closely, notice that they all have four carbons in a straight line here, 4 carbons. However, what makes them different is whether the fluorine is touching a double bond carbon, an sp2 carbon, or is it bonded to an sp3 carbon? See, that's the difference here. So it's a connection difference. Fluorine is not connected exactly the same in both of these molecules. So, and the same with the hydrogen as well. So that's what makes these constitutional. This fluorine and this hydrogen, see how we have a fluorine here and let's say a hydrogen here. So we're replacing the position of those two groups. Whenever you reconnect things differently, that is constitutional isomers. Okay? So that's what you need to know for constitutional. Stereoisomers is where we have the same connections. There's no difference. So notice how there's 4 carbons, there's 4 carbons, right? There's a fluorine on a double bond carbon, fluorine on a double bond. Everything's connected the same way. So there's no difference in connection. But what is different is the arrangement in space. See, an alkene doesn't have rotation. So this is an important thing to remember. When you have a double bond, it prohibits rotation. So these p orbitals are going to restrict rotation. But if you have a single bond, it has complete rotation. You could take two atoms that are connected by a single bond and they could completely rotate around that single bond. Double bond doesn't have that. So the fact that this is a double bond over here, so we have this double bond right here, that restricts rotation. So if we have a methyl, a CH3 and a CH3, and they're on the same side, you could not spin it around to get them on opposite sides. If it was an alkane, you can, but not an alkene. So this is an example of stereoisomers. They're known as cis-trans isomers, and we'll learn more about that after this exam. So these are stereoisomers because they have the same connections. They're only differing in spatial arrangement. Okay? Now, we'll see another example of stereoisomers, which is very similar to this on the next page. But for now, this is enough of an understanding. So realize from this page that isomer is where you have molecules that have the same formula, but they're not the same. They're either not the same because they're connecting differently, or they're not the same because of some spatial arrangement, and that's the two type of isomers. One last point about the connecting differently. Let's say I have a C with 3 H's, another carbon with 2 H's, and then an oxygen with an H. So this is an alcohol, right? We know that this is an alcohol because it's a OH on an sp3 carbon. But what if I instead were to take that oxygen, put it in the middle, and now I have something that looks like this. If you look closely, they have the exact same formula. They both have C2H6, C2H6O. So these two have the exact same formula, but they're not the same, right? This is an alcohol, and this is an ether. So that's another example of connectivity differences, okay? Just want to make sure it's clear because this one was already drawn out, and now we did one from scratch. I drew it out while I explained it to you. All right. Now we get into what we really need to know for this exam, and that is, how do you draw these isomers? Well, the first thing is we need to know how to identify cis from trans in a very basic way. Cis and trans actually can get complicated, but in our case, we need to know it in a simple way. And that is, if we look at an alkene, and each carbon of the alkene is going to have 2 groups that are, so, well, let me say it this way. They both have an H each, 1 H each. So this one has a hydrogen, and that one has a hydrogen. And then something else. It doesn't matter what the other 2 things are. So if we have an alkene and we have H and let's say A and B, it doesn't matter what they are, then we can consider this to be cis or trans. What we could do is 2 things, one of 2 ways. You could either look at the H's and ask whether they're on the same or opposite side, or look at the AB and ask if they're on the same or opposite side. It doesn't matter as long as you're consistent. So look at the H's or look at the AB part. So in this case here, since I already circled the H's, notice how the H's are both up above and there's no rotation, right? So this is known as cis because the group of reference, either the 2 H's or whatever other 2 groups that they give you, are on the same side. Now, notice how here the H and this H are on opposite sides. And that means that the other 2 groups, the methyls, are on opposite sides. So that makes trans. Trans is when they're on opposite sides of the double bond. So if you look at the double bond and just think of it as having an above and below area, if the 2 groups, the 2 H's or the 2 other groups, are on the same side, above or below, then they're cis. And if they're on opposite side, they're trans. That's what you need to know for this isomerism. Now, here's the interesting idea. Can cis molecules become trans molecules? So if I have, let's say, an alkene, and let's say I'm going to put a CH3 here and a CH3 there. Now, first of all, let me point something out. You see how I'm drawing this with this alkene? I'm not showing the H's, but you know each carbon should have 4 bonds. So right now, that carbon on the left and on the right, they only have 3 bonds. That means they must have H's, 1 H each. You always want to build carbon up to 4 bonds, unless it's charged. Then it would be just 3 bonds. Okay, otherwise you always got to get it to 4. So remember, alkenes are 120 planar sp2. So that means that if they have a bond up, they have a bond down. If they have a bond to the left, they have a bond to the right. That's how it works. Okay, so sp2 carbons are going to have an up-down bond or a left-right bond. So since there's a down bond, this is pointing down, then there must be an up H, like that. And since that one's pointing down, below the alkene, there must be an up H. Okay, so I just want to show you how to fill in the H's if you need to see them. In this case, you really didn't need to see the H's. But now let's go to the question. Can cis become trans? Well, the problem with turning a cis into trans, so what I did is I just changed the methyl to point it up on the right. The problem here is that there's no rotation. However, do you remember we have these antibonding orbitals that I went all into details in chapter 1? Antibonding orbitals are empty. So if you were able to take the double bond, the electrons in that double bond, and you were somehow able to promote one of them into the antibonding, then they're no longer a double bond. See that? So remember how, like, if you have an alkene, the alkene's going to have, for that, let's say that pi bond, it's going to have 2 p orbitals, right? So we have these 2 p orbitals here. Well, let me actually shade on the same side. So let's do this. Now, when they come together,